Hello everyone, here are videos for civil engineering. Welcome to the channel Amazing Civil Engineering Studies. Here we have different videos on all topic of civil engineering. Please subscribe and press bell icon, like and share as many as possible. Geo-technical engineering, soil. Introduction, soil formation, soil types, and phase relations of soils. Introduction. The term soil can have different meanings, depending upon the field in which it is considered. To a geologist, it is the material in the relative thin zone of the Earth's surface within which roots occur, and which are formed as the products of past surface processes. The rest of the crust is grouped under the term rock. To a pedologist, it is the substance existing on the surface, which supports plant life. To an engineer, it is a material that can be built on foundations of buildings, bridges, built in basements, culverts, tunnels, built with embankments, roads, dams, supported, retaining walls. Soil mechanics is a discipline of civil engineering involving the study of soil, its behavior, and application as an engineering material. Soil mechanics is the application of laws of mechanics and hydraulics to engineering problems dealing with sediments and other unconsolidated accumulations of solid particles, which are produced by the mechanical and chemical disintegration of rocks. Regardless of whether or not they contain an admixture of organic constituents. Soil consists of a multi-phase aggregation of solid particles, water, and air. This fundamental composition gives rise to unique engineering properties, and the description of its mechanical behavior requires some of the most classic principles of engineering mechanics. Engineers are concerned with soil's mechanical properties, permeability, stiffness, and strength. These depend primarily on the nature of the soil grains, the current stress, the water content and unit weight. Formation of soils. Soil is formed from rock due to erosion and weathering action. Igneous rock is the basic rock formed from the crystallization of molten magma. This rock is formed either inside the earth or on the surface. These rocks undergo metamorphism under high temperature and pressure to form metamorphic rocks. Both igneous and metamorphic rocks are converted into sedimentary rocks due to transportation to different locations by the agencies such as wind, water, etc. Finally, near the surface, millions of years of erosion and weathering converts rocks into soil. Soils are formed from materials that have resulted from the disintegration of rocks by various processes of physical and chemical weathering. The nature and structure of a given soil depends on the processes and conditions that formed it. Breakdown of parent rock, weathering, decomposition, erosion. Transportation to site of final deposition, gravity, flowing water, ice, wind. Environment of final deposition, flood plain, river terrace, glacial moraine, lacustrine or marine. Subsequent conditions of loading and drainage, little or no surcharge, heavy surcharge due to ice or overlying deposits, change from saline to fresh water, leaching, contamination. All soils originate, directly or indirectly, from different rock types. Weathering. Physical weathering reduces the size of the parent rock material, without any change in the original composition of the parent rock. Physical or mechanical processes taking place on the Earth's surface include the actions of water, frost, temperature changes, wind, and ice. They cause disintegration and the products are mainly coarse soils. The main processes involved are exfoliation, unloading, erosion, freezing, and thawing. The principal cause is climatic change. In exfoliation, the outer shell separates from the main rock. Heavy rain and wind cause erosion of the rock surface. Adverse temperature changes produce fragments due to different thermal coefficients of rock minerals. The effect is more for freeze-thaw cycles. Chemical weathering. Chemical weathering not only breaks up the material into smaller particles but alters the nature of the original parent rock itself. The main processes responsible are hydration, oxidation, and carbonation. New compounds are formed due to the chemical alterations. Rainwater that comes in contact with the rock surface reacts to form hydrated oxides, carbonates, and sulfates. If there is a volume increase, the disintegration continues. Due to leaching, water-soluble materials are washed away and rocks lose their cementing properties. Chemical weathering occurs in wet and warm conditions and consists of degradation by decomposition and/or alteration. The results of chemical weathering are generally fine soils with altered mineral grains. The effects of weathering and transportation mainly determine the basic nature of the soil, size, shape, composition, and distribution of the particles. The environment into which deposition takes place, and the subsequent geological events that take place there, determine the state of the soil, density, moisture content, and the structure or fabric of the soil, bedding, stratification, occurrence of joints or fissures. Transportation agencies can be combinations of gravity, flowing water or air, and moving ice. In water or air, the grains become sub-rounded or rounded, and the grain sizes get sorted so as to form poorly graded deposits. In moving ice, grinding and crushing occur. Size distribution becomes wider, forming well-graded deposits. Transportation agencies can be combinations of gravity, flowing water or air, and moving ice. In water or air, the grains become sub-rounded or rounded, and the grain sizes get sorted so as to form poorly graded deposits. In moving ice, grinding and crushing occur. Size distribution becomes wider, forming well-graded deposits. In running water, soil can be transported in the form of suspended particles, or by rolling and sliding along the bottom. Coarser particles settle when a decrease in velocity occurs, whereas finer particles are deposited further downstream. In still water, horizontal layers of successive sediments are formed, which may change with time, even seasonally or daily. Wind can erode, transport and deposit fine-grained soils. Wind-blown soil is generally uniformly graded. A glacier moves slowly but scours the bedrock surface over which it passes. Gravity transports materials along slopes without causing much alteration. Soil types. Soils as they are found in different regions can be classified into two broad categories. Residual soils. Transported soils. Residual soils are found at the same location where they have been formed. Generally, the depth of residual soils varies from 5 to 20 m. Chemical weathering rate is greater in warm, humid regions than in cold, dry regions, causing a faster breakdown of rocks. Accumulation of residual soils takes place as the rate of rock decomposition exceeds the rate of erosion or transportation of the weathered material. In humid regions, the presence of surface vegetation reduces the possibility of soil transportation. As leaching action due to percolating surface water decreases with depth, there is a corresponding decrease in the degree of chemical weathering from the ground surface downwards. Residual soils are formed from the weathering of rocks and practically remain at the location of origin with little or no movement of individual soil particles. This results in a gradual reduction of residual soil formation with depth, until unaltered rock is found. Residual soils comprise of a wide range of particle sizes, shapes and composition. Important points related to residual soil. Weathering, due to climate effects, and leaching of water-soluble materials in the rock are the geological processes in the formation of these soils. The rate of rock decomposition is greater than the rate of erosion or transportation of weathering material and results in the accumulation of residual soil. As the leaching action decreases with depth, there is a progressively lesser degree of rock weathering from the surface downwards, resulting in reduced soil formation, until one finally encounters unaltered rock. Residual soil generally comprise a wide range of particle sizes, shapes, and composition. In general, the rate of weathering is greater in warm, humid regions than in cold, dry regions. Humid, warm regions are favorable to chemical weathering. Depth of residual soils varies from 6 to 25 meters in general and from 7.5 to 15 meters in South India. Transported soils. Weathered rock materials can be moved from their original site to new locations by one or more of the transportation agencies to form transported soils. Transported soils are classified based on the mode of transportation and the final deposition environment. Soils that are carried and deposited by rivers are called alluvial deposits. Soils that are deposited by flowing water or surface runoff while entering a lake are called lacustrine deposits. Alternate layers are formed in different seasons depending on flow rate. If the deposits are made by rivers in sea water, they are called marine deposits. Marine deposits contain both particulate material brought from the shore as well as organic remnants of marine life forms. Melting of a glacier causes the deposition of all the materials scoured by it, leading to formation of glacial deposits. Soil particles carried by wind and subsequently deposited are known as aeolian deposits. Water-transported soil. Swift-running water is capable of moving a considerable volume of soil. Soil may be transported in the form of suspended particles or by rolling and sliding along the bottom of the stream. The size of the particle that can be in suspension is related to the square of the velocity of the flowing water. Particles transported by water range in size from boulders to clay. Coarser particles are dropped when a decrease in water velocity occurs as the stream or river deepens, widens, or changes direction. Fine particles still remain in suspension and get deposited in quieter waters downstream. This is a typical case of a stream moving downhill, passing over a valley, and ultimately reaching a large body of water. Soils that are carried and deposited by rivers are called alluvial deposits. Glacial deposits. Compaction and recrystallization of snow lead to the formation of glaciers. Glacier growth and movement depend on the formation of ice. Glacial deposits form a very large group of transported soil. A glacier moves extremely slowly but deforms and scours the surface and the bedrock over which it passes. Melting of a glacier causes deposition of all the materials, and such a deposit is referred to as till. The landform or topographic surface after a glacier has receded is called a ground moraine or till plain. Soils deposited by the surface and subsurface glacial rivers that remain in the form of long winding ridges are called eschers. They may vary from about 10 to 30 meters in height and about 0.5 kilometers to several kilometers in length. Isolated mounds of glacial debris varying from about 10 to 70 inches in height and 200 to 800 meters in length are called drumlins. Large boulders picked up by a glacier, transported to a new location, and dropped are called erratic. In many locations, it is often found that the material is dense and contains considerable sand and gravel. It is believed that glaciers covered a large portion of the land during the Ice Age. Wind-transported soils. Like water, wind can erode, transport, and deposit fine-grained soils. Soils carried by wind are subsequently deposited as aeolian deposits. Dunes are formed due to the accumulation of such wind-deposited sands. Dunes are a rather common occurrence in the desert areas of Africa, Asia, and the USA. Sands from dunes may be used to a limited extent for construction purposes. Fine-grained soils such as silts and clays can be transported by wind in arid regions. Wind-blown silts and clays deposited with some cementing minerals in a loose, stable condition are classified as loess. Loess deposits have low density, high compressibility, and poor bearing resistance when are in wet condition. Loess is an elastic sediment comprising a uniformly sorted mixture of silt, fine sand, and clay-size particles. The structure of a loess deposit is susceptible to collapse on saturation. Gravity deposits. Gravity can transport materials only for a short distance. As the movement is limited, there is no appreciable change in the materials moved. Gravity deposits are termed tailless. They include the material at the base of cliff and landslide deposits. The tailless material at the cliff is formed due to the disintegration and subsequent failure of the cliff face. These fragments are generally loose and porous. Swamp and marsh deposits. In water-stagnated areas where the water table is fluctuating, and vegetational growth is possible, swamp and marsh deposits develop. Soils transported and deposited under this environment are soft, high in organic content, and unpleasant in odor. Accumulation of partially or fully decomposed aquatic plants in swamps or marshes is termed muck or peat. Muck is a fully decomposed material, spongy, light in weight, highly compressible, and not suitable for construction purposes. Phase relations of soils. Soil is not a coherent solid material like steel and concrete, but is a particulate material. Soils, as they exist in nature, consist of solid particles, mineral grains, rock fragments, with water and air in the voids between the particles. The water and air contents are readily changed by changes in ambient conditions and location. As the relative proportions of the three phases vary in any soil deposit, it is useful to consider a soil model which will represent these phases distinctly and properly quantify the amount of each phase. A schematic diagram of the three-phase system is shown in terms of weight and volume symbols respectively for soil solids, water, and air. The weight of air can be neglected. The soil model is given dimensional values for the solid, water and air components. Total volume V equals V S and V W and V V. Three-phase system. Soils can be partially saturated, with both air and water present, or be fully saturated. No air content, or be perfectly dry, no water content. In a saturated soil or a dry soil, the three-phase system thus reduces to two phases only, as shown. The various relations can be grouped into volume relations, weight relations, interrelations, volume relations. As the amounts of both water and air are variable, the volume of solids is taken as the reference quantity. Thus, several relational volumetric quantities may be defined. The following are the basic volume relations. Void ratio, E, is the ratio of the volume of voids, V, to the volume of soil solids, V, S, and is expressed as adsimal. E equals V, VV, S. Porosity, N, is the ratio of the volume of voids to the total volume of soil, V, and is expressed as a percentage. N equals V. V/V times 100 void ratio and porosity are interrelated to each other as follows. E equals N/1 minus N, and N equals E/1 plus E. The volume of water, V W, in a soil can vary between 0, i.e. a dry soil, and the volume of voids. This can be expressed as the degree of saturation, S, in percentage. S equals V W/V. V times 100 for a dry soil, S equals 0%, and for a fully saturated soil, S equals 100%. Air content, A. C, is the ratio of the volume of air, V A, to the volume of voids, A. C equals V A/V. V percentage air voids, N. A is the ratio of the volume of air to the total volume. N A equals V A. V times 100 equals N times A. C. Weight relations. Density is a measure of the quantity of mass in added volume of material. Unit weight is a measure of the weight of a unit volume of material. Both can be used interchangeably. The units of density are ton m superscript 3, kg m superscript 3, or gcm superscript 3. The following are the basic weight relations. The ratio of the mass of water present to the mass of solid particles is called the water content, W, or sometimes the moisture content. W equals W. W/W. S. The mass of solid particles is usually expressed in terms of their particle unit weight. S, or specific gravity, G. S, of the soil grain solids. S equals W. S/V. S equals G. S. W. Where W equals unit weight of water for most inorganic soils, the value of G. S lies between 2.60 and 2.80. The presence of organic material reduces the value of G. S. Dry unit weight, D, is a measure of the amount of solid particles per unit volume. D equals W SV. Bulk unit weight T or is a measure of the amount of solid particles plus water per unit volume. T equals W SNW W slash V SNV V. Saturated unit weight SAT is equal to the bulk density when the total voids is filled up with water. Buoyant unit weight, or submerged unit weight, is the effective mass per unit volume when the soil is submerged below standing water or below the groundwater table. Equals SAT minus W. Interrelations. It is important to quantify the state of a soil immediately after receiving in the laboratory and prior to commencing other tests. The water content and unit weight are particularly important, since they may change during transportation and storage. Some physical state properties are calculated following the practical measurement of others. For example, dry unit weight can be determined from bulk unit weight and water content. The following are some interrelations. W equals dot equals dot equals dot equals plus dot 1 plus equals 1 plus dot W1 plus D equals one plus D equals 1 plus equals minus 1 plus 1 dot W1 plus equals minus 1 W1 plus. These are some interrelations. Try to solve these numerical using above relationship. Example 1. A soil has void ratio equals 0.72, moisture content equals 12% and GS equals 2.72. Determine its A. Dry unit weight b. Moist unit weight, and the c. Amount of water to be added per m3to make it saturated. Use W equals 9.81 kN m3. Example 2. The dry density of a sand with porosity of 0.387 is 1,600 kg m3. Find the void ratio of the soil and the specific gravity of the soil solid state. W equals 9.81 kN m3. N equals 0.387. D equals 1600 kg m3. Soil classification. It is necessary to adopt a formal system of soil description and classification in order to describe the various materials found in ground investigation. Such a system must be meaningful and concise in an engineering context, so that engineers will be able to understand and interpret. It is important to distinguish between description and classification. Description of soil is a statement that describes the physical nature and state of the soil. It can be a description of a sample, or a soil in situ. It is arrived at by using visual examination, simple tests, observation of site conditions, geological history, etc. Classification of soil is the separation of soil into classes or groups, each having similar characteristics and potentially similar behavior. A classification for engineering purposes should be based mainly on mechanical properties, permeability, stiffness, strength. The class to which a soil belongs can be used in its description. The aim of a classification system is to establish a set of conditions which will allow useful comparisons to be made between different soils. The system must be simple. The relevant criteria for classifying soils are the size distribution of particles and the plasticity of the soil. For measuring the distribution of particle sizes in a soil sample, it is necessary to conduct different particle size tests. Wet sieving is carried out for separating fine grains from coarse grains by washing the soil specimen on a 75 micron sieve mesh. Dry sieve analysis is carried out on particles coarser than 75 micron. Samples, with fines removed, are dried and shaken through a set of sieves of descending size. The weight retained in each sieve is measured. The cumulative percentage quantities finer than the sieve sizes, passing each given sieve size, are then determined. The resulting data is presented as a distribution curve with grain size along x-axis, log scale, and percentage passing along y-axis, arithmetic scale. Sedimentation analysis is used only for the soil fraction finer than 75 microns. Soil particles are allowed to settle from a suspension. The decreasing density of the suspension is measured at various time intervals. The procedure is based on the principle that in a suspension, the terminal velocity of a spherical particle is governed by the diameter of the particle and the properties of the suspension. In this method, the soil is placed as a suspension in a jar filled with distilled water to which a deflocculating agent is added. The soil particles are then allowed to settle down. The concentration of particles remaining in the suspension at a particular level can be determined by using a hydrometer. Specific gravity readings of the solution at that same level at different time intervals provide information about the size of particles that have settled down and the mass of soil remaining in solution. The results are then plotted between % finer, passing, and log size. Grain size distribution curve. The size distribution curves, as obtained from coarse and fine-grained portions, can be combined to form one complete grain size distribution curve, also known as grading curve. A typical grading curve is shown. From the complete grain size distribution curve, useful information can be obtained such as grading characteristics which indicate the uniformity and range in grain size distribution. Percentages, or fractions, of gravel, sand, silt, and clay size. Grading characteristics. A grading curve is a useful aid to soil description. The geometric properties of a grading curve are called grading characteristics. To obtain the grading characteristics, 3 points are located first on the grading curve. D 60 equals size at 60% finer by weight. D 30 equals size at 30% finer by weight. D 10 equals size at 10% finer by weight. Formation of clay minerals. A soil particle may be a mineral or a rock fragment. A mineral is a chemical compound formed in nature during a geological process, whereas a rock fragment has a combination of one or more minerals. Based on the nature of atoms, minerals are classified as silicates, aluminates, oxides, carbonates, and phosphates. Out of these, silicate minerals are the most important as they influence the properties of clay soils. Different arrangements of atoms in the silicate minerals give rise to different silicate structures. Basic structural units. Soil minerals are formed from two basic structural units, tetrahedral and octahedral. Considering the valencies of the atoms forming the units, it is clear that the units are not electrically neutral and as such do not exist as single units. The basic units combine to form sheets in which the oxygen or hydroxyl ions are shared among adjacent units. Three types of sheets are thus formed, namely silica sheet, gibbsite sheet, and brucite sheet. Isomorphous substitution is the replacement of the central atom of the tetrahedral or octahedral unit by another atom during the formation of the sheets. The sheets then combine to form various two-layer or three-layer sheet minerals. As the basic units of clay minerals are sheet-like structures, the particle formed from stacking of the basic units is also plate-like. As a result, the surface area per unit mass becomes very large. Structure of clay minerals. A tetrahedral unit consists of a central silicon atom that is surrounded by 4 oxygen atoms located at the corners of a tetrahedron. A combination of tetrahedrons forms a silica sheet. An octahedral unit consists of a central ion, either aluminum or magnesium, that is surrounded by 6 hydroxyl ions located at the corners of an octahedron. A combination of aluminum hydroxyl octahedrons forms a gibbsite sheet, whereas a combination of magnesium hydroxyl octahedrons forms a brucite sheet. Two-layer sheet minerals. Kaolinite and halloysite clay minerals are the most common. Kaolinite mineral. The basic kaolinite unit is a two-layer unit that is formed by stacking a gibbsite sheet on a silica sheet. These basic units are then stacked one on top of the other to form alloys of the mineral. The units are held together by hydrogen bonds. The strong bonding does not permit water to enter the lattice. Thus, kaolinite minerals are stable and do not expand under saturation. Kaolinite is the most abundant constituent of halloysite mineral. The basic unit is also a two-layer sheet similar to that of kaolinite except for the presence of water between the sheets. Montmorillonite and illite clay minerals are the most common. A basic three-layer sheet unit is formed by keeping one silica sheet each on the top and at the bottom of a gibbsite sheet. These units are stacked to form alloys as shown. Montmorillonite mineral. The bonding between the three-layer units is by van der Waals forces. This bonding is very weak and water can enter easily. Thus, this mineral can imbibe a large quantity of water causing swelling. During dry weather, there will be shrinkage. Illite mineral. Illite consists of the basic montmorillonite units but are bonded by secondary valence forces and potassium ions, as shown. There is about 20% replacement of aluminum with silicon in the gibbsite sheet due to isomorphous substitution. This mineral is very stable and does not swell or shrink. Fine soil fabric. Clay particles are flaky. Their thickness is very small relative to their length and breadth, in some cases as thin as 1/100 th of the length. They therefore have high specific surface values. These surfaces carry negative electrical charge, which attracts positive ions present in the pore water. Thus a lot of water may be held as adsorbed water within a clay mass. Natural soils are rarely the same from one point in the ground to another. The content and nature of grains varies, but more importantly, so does the arrangement of these. The arrangement and organization of particles and other features within a soil mass is termed its fabric. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.